Today's topic is kinetics and equilibria. Just a reminder, this content is geared toward the high school student, but if you've attended as a middle schooler, we encourage you to hang in there and use it as a learning experience. Content may be a little bit more challenging for you, but it's never too early to get exposed to the wonderful world of science. If you're new to our labs, we have set up a new email address, flynn@home@flynnsci.com for your feedback. So please provide your comments at the end of the session via email. During this live lab, everyone will be on mute with the ability to ask questions of the Flynn team by selecting the QA button on the bottom of the screen. We'll attempt to answer all questions and we'll select a handful to be answered live at the end of the session. Please take note, the chat function is really for IT purposes only. It's only seen by us here at Flynn. And we ask that all questions around the content please be sent to us using the QA button at the bottom of the screen. We're also joined today by our good friend, Lenny Friedhoff, a semi-retired chemistry teacher who's going to be monitoring the Q&A panel for us and giving great answers back to the students and teachers as they come in. So with that, I'm going to turn things over to our senior scientist here at FlinnScientific, Mike Marble.
Yeah, thanks, Dan, and thanks everyone for being with us. I'll second what Dan said. This is these unique times, and we're trying to bring you this unique solution. So before I dive into the science, I want to show you a little bit about how the program works if you're a student or a teacher. So I'm going to just hop out of the presentation and pop open an internet window. If you're looking for the documents that are associated with these live labs, you can go to our website and navigate to the Flynn at-home science landing page. Once there, you'll see we have an at-home lab series button here. And each of these labs has teacher materials and student documents associated with them that you can download or use in Google Doc form and write directly into them. So if you're using this kinetics lab today and you're a student, you can go to the student documents hyperlink. This will bring you into a Google folder, and you've probably worked with some of these in the past. Each of these Google folders houses a video and a student worksheet and some sample student data. So essentially everything you need to complete a lab experience without actually physically manipulating equipment. Now, a couple points, and bear with me here. If you've done this before, this is going to be redundant for you. But you can, if you want to, download Google Docs as Word documents and as PDF documents if you're not comfortable with the Google format. Alternatively, you can make copies of any Google Doc into your own Google folder, at which point the document becomes yours and you can write in it. Okay, so that's all there for you. So with that out of the way, I want to get to the presentation. And this is something that's really near and dear to my heart. This is something that Kinetics and Equilibria, we can look around the natural world and find examples of these things everywhere. And kinetics is really about how fast or slow reactions happen. So I want to just start out, instead of me talking about it, just show you a quick video to kind of delineate the difference between something that's fast and something that's slow. And we can then, from there, get into the experiment. So I'm going to play this for you, and I'll preface this by saying I'm going to post these videos into the folder I just showed you afterwards. So if you experience some chop or some lag time between the audio and video, you can go back and watch these on your own machine.
Chemical kinetics is all about how fast or slow reactions occur. Here's an example of a fast reaction. I'm going to go ahead and drop some sodium in this flask, which has a layer of oil on top and a layer of water on the bottom. As soon as the sodium comes in contact with the water, a reaction occurs. It is a very fast process. The sodium doesn't sit there on top of the water for 5 minutes and then react. It happens right away. When the two chemicals combine, the reaction is instantaneous and results in the production of sodium hydroxide and hydrogen gas. In contrast, the reaction of iron with oxygen to form iron oxide happens very slowly, in some cases over years, particularly if there's no moisture to help the reaction along. So, you see this nail sitting on the desk here with ample oxygen in the air all around it? Nothing happens. It doesn't rust. At least nothing happens with any great speed. The reaction is happening, but incredibly slowly, and your eyes don't even register a change. This is kinetics.
So there you go. There's a nice kind of brief introduction to kinetics, and think about, go look in your refrigerator and think about why you have a refrigerator. Those cold temperatures are slowing down some of the decomposition reactions that happen around food. Okay, so the first thing I want to get to here is the first part of the lab where you were meant to demonstrate, your teacher was meant to demonstrate the decomposition of hydrogen peroxide. Okay, and this is something that you probably have in your medicine cabinet. Now, I'll point out that in this demonstration, we're going to decompose 30% hydrogen peroxide. In contrast, the stuff you buy in a grocery store is 3%. So this is a much higher concentration. Okay, we're going to add a catalyst to decompose it. And I just want you to observe, again, what a fast reaction like this looks like.
Catalysts are compounds we add to reactions to speed them up. They do not react and are not consumed. They only serve to move things along. I have here an example of how catalyst works. In this flask, I have hydrogen peroxide. Over time, hydrogen peroxide decomposes into hydrogen and oxygen gas, but the reaction happens very slowly. If I add a catalyst, however, in this case sodium iodide, watch what happens. This flask has also got some soap in it to make the gas bubbles visible. You see how much the addition of the catalyst made that reaction speed up? So remember, a catalyst is something that increases the rate of reaction but is not consumed during the reaction.
Okay, so there is another example of a chemical reaction, and you can see that it happens at a particular measurable speed. You know, you could actually qualitatively take a stopwatch and count how long that takes. Okay, and again, I should say again, if you're having trouble with the audio visual, I'm going to post these videos into the folder afterwards. Okay, so now what I want to get to is the biggest part of the experiment, where we're meant to come up with a controlled experiment to study the decomposition of hydrogen peroxide. Okay, so the example you just saw, we decomposed 30% hydrogen peroxide. Okay, so very concentrated. Now, the purpose of this lab was to design a procedure to study the effect of peroxide concentration on the reaction rate of that decomposition. And if you're in lab, you'd have enough materials to conduct 3 trials. Okay, so what I want to do is, before we do this lab, before we kind of come up with this, I want to think about, think about what your independent variable would be, what your control variable would be, and what your dependent variable would be. If you're designing an experiment to measure the effect of concentration on the decomposition of hydrogen peroxide, okay? And for this one, okay, I'm going to show you. So on screen here, what you see is you see our teacher has 3 graduated cylinders, okay? Actually, I should say they're not really graduated cylinders. They don't have markings on them. So they're 3 flasks, okay? These are borosilicate to withstand high temperature. So in each of these flasks, there is a different concentration of hydrogen peroxide, okay? So in order to study the effect of concentration of hydrogen peroxide on the reaction rate, we're going to vary the concentration and observe how fast or how slow a reaction takes to occur. Okay, so I'm going to play you this video in snippets, okay, and we're going to kind of stop this, pause it, and think about what we see along the way, okay? So in each case, we're adding a catalyst, sodium iodide, to hydrogen peroxide to observe the decomposition. So, and I've taken away the audio from this, so you won't hear any audio, but let's observe this first reaction. So she's adding her catalyst to hydrogen peroxide and just get a qualitative feel for how fast this reaction occurs. So think about this in contrast to the first demonstration you saw, where we added sodium iodide to hydrogen peroxide and you formed a giant poof right before your eyes very quickly. In contrast, this seems to be happening fairly slowly, right? There's not this very vigorous reaction. You can see it decomposing there as we zoom in, but it's not instantaneously overflowing. And now we go to our other flask here, and we're going to pour our sodium iodide in here. Now, this is a different concentration of hydrogen peroxide in this flask. Let's see what the result is. So you can see qualitatively here that this is proceeding faster. Okay, so ask yourself, do you think that the concentration of hydrogen peroxide in this flask is lower or higher than the concentration in the previous flask? Okay, so now we're going to keep going, and again, you can see this kind of rising steadily, but it's not going crazy fast, it's not overflowing. And now we're going to go ahead to our highest concentration and see what happens here. So now we're going to add our catalyst to a high concentration, and now you see how fast that goes relative to the other ones. So you can see kind of a marked difference in reaction rate across the three concentrations, okay? So at this point, before we get into the results and really analyzing the results, I want to ask poll question 1, Dan, in terms of kind of thinking about this experimental design. Could you put up poll question 1?
Yep, Mike, I can.
Thank you.
Second.
And as Dan's doing that, so remember, in each of our 3 flasks here, oh, sorry, Dan.
This is the wrong one, I'm sorry. Having an issue here.
Oh, that's all right. Take your time. So it's poll question 1. And as Dan's doing that, remember what we did. We had 3 separate flasks. Each flask contained a controlled amount of hydrogen peroxide. So across each flask, we controlled the amount of hydrogen peroxide. We kept it the same, but the concentration was different in each. And then we added the same amount of catalyst.
Mike, is that poll up yet?
It's not, no.
Okay, I'm having a deployment issue. Give me another second here.
Sure, yeah.
I don't know why. Doing it the same way I've done it the last 7 times.
No, that's all right. While we're waiting for the question, think about I'll tell you the question. What's the independent variable in this experiment? What is the independent variable? If we don't get the question to deploy, we can answer it kind of the old-fashioned analog way. So take a second to think to yourself, you know, we're studying the effect of concentration on reactant rate. What's the independent variable in this experiment that you just saw?
Yep, there it is. Everybody see that?
I'm not seeing it. Why don't you try it one more time, Dan?
I will give it a shot. Some person was able to see it, responded. Maybe it was a panelist view. Hang on, everybody. My apologies.
There we go.
Is that still can't see it, Mike?
I can see it, but I'm seeing it with the results. So I think you just need to redeploy it so that people can answer it.
There's got to be a delay in the system because I'm seeing it on my end. Could be a bandwidth issue here.
Okay. Well, that's okay. Again, if try it one more time. If we don't get it, we'll answer it the old-fashioned way. What is the independent variable? There we go. It's up there now, Dan.
All right. Apologies, class.
So we'll give people who have been thinking about this, give it another 15 seconds. And this is really the heart of the experiment, right? We're meant to design an experiment to determine the effects of concentration on reaction rate. What was the independent variable here? How are we looking today, Dan? How's the class?
We're split here between the 2 middle ones, but we got a pretty good response right here. So I'm going to end the polling.
Yeah.
Let's keep our fingers crossed that the results share properly.
All right. Well, we're in for a real, I guess, a treat in some way, right? So think about an independent variable is something that you intentionally manipulate, that you, the experimentalist, are intentionally in charge of manipulating. You have to be able to manipulate it, okay? So in this case, the independent variable, when we did this experiment, we intentionally varied the concentration of hydrogen peroxide. We were exerting some control over manipulation. Now, some people identified reaction speed here, where the reaction speed in this case is the dependent variable. That was kind of the, so at one point, I've been talking a lot about different exams the past few days. For any of you, anybody on the call who's going to be taking an ACT science exam, they tend to focus on this sort of thing on a question or two. So just a good thing to know for that, just as an aside. Okay, but independent variable is concentration of the peroxide. Now, I already gave away poll question 2. Let's put up poll question 5, Dan. Poll question 5. See what people think about that.
All right, here we go.
What describes that decomposition? And this is a question that if you had joined us last week for chemical reactions, we asked this a number of different ways. So we're kind of coming back here to try to get stuff to connect throughout the different experiences.
We definitely have a runaway here. We had about 70% really active participants today in the class. This is fantastic. We have a consensus on this one, Mike. So we're going to end it. Looks like chemical change is far and away the winner.
80% say chemical change. Very good. That's the right answer. So a quick way as you go forward to differentiate between chemical and physical change. Chemical change is something that's generally not as easy to reverse as a physical change. Physical change is something like melting ice. You can melt ice, take it from the solid state to the liquid state, but then you could refreeze that liquid state water. So reversible process, whereas chemical is not. Okay, so nice job there. Now, here's a higher level of difficulty question before we move on. If you don't know what hydrogen peroxide decomposes into, I'll tell you afterwards, but I want to ask poll question 6, and this is getting at, do you really have a good understanding of what the decomposition products of hydrogen peroxide are, Dan? So could you put up the last question around this is question number 6.
All right. Should be able to see it. No?
Not just yet.
There is bad delay going on.
Yeah, the Zoom stock has fallen, Dan.
Is that what it is? I'm starting to think that's the reason why. Try it here. Let's go.
So here we go. It's up there now.
Okay.
So here, let me add some color to this question before you answer, because we're going to see this example after you answer the question. So let's say we ignite a wood splint, blow it out. Will that wood splint reignite or not upon immersion in the products of hydrogen peroxide decomposition? Is there something, a byproduct of hydrogen peroxide decomposition, that will support combustion? And then we're going to see what the result is. I honestly don't know what to expect of this one, Dan. I'm up in the air.
Well, it's based on the audience. I'm going to say it's why I'm hosting and you're teaching, because I would have said no. Oh. So we'll see. We do have a majority here, so I'm going to end the polling and share the results.
Yeah. So the right answer is yes. So let's see this real quick. I just want to kind of fast forward here. I'm going to play you this video. And at the end of this, you'll see Irene here. This is our presenter, and you won't hear audio here, but she's ignited a wood splint. She's going to extinguish it, and she can be rather verbose. And then she's going to place it back in the, and I think I stopped the video there. She's going to place it back in. And in fact, the splint here, I don't think I extended the video long enough, but it will reignite because one of the products of hydrogen peroxide decomposition is oxygen. So when you decompose hydrogen peroxide, you get oxygen and water, okay? So here were essentially the results of our experiment. And these, you can use these to go back and complete your student worksheet if you haven't already, these results. But what we did in our experiment was, with the materials afforded to us, we decided we'll start out with 2.5% peroxide, 5%, and 10%. And we controlled the amount of hydrogen peroxide in our experiment. In other words, in each flask, we used the same volume of hydrogen peroxide. We used the same concentration of catalyst, of iodide, and we used the same amount. And we saw that as reactant concentration increased, so did reaction speed, okay? So think about why that's the case. To kind of get back to this idea, I want to show you this video which explains how this idea of reactant concentration bears on reaction speed, okay? And this gets to what we call collision theory.
One of the fundamental things to realize about reactions is that molecules have to come in contact with each other to react. This idea is often called collision theory. And collision theory tells us that it is not enough for molecules to simply collide. They have to collide in the right way to react. There are a few things you can do to help collisions be successful and lead to a reaction. First, you can increase the temperature. This causes molecules to move faster, and so the number of collisions increases and the chance for successful ones as well. For example, if you have ever taken a ride in bumper cars at an amusement park, you know that the faster you go, the more likely you are to bounce into another car.
So that's a nice example I like to bring up with respect to kinetics. Most people have been, I haven't been in a while, but most people have been in bumper cars at some point in their childhood. And if you're in a little bumper car ring and all the bumper cars are going really fast, you're going to increase the probability of a collision. And that's what really needs to happen for a chemical reaction to occur. Molecules need to come together and collide. The other thing, if you put more bumper cars in the ring, you're going to increase the probability of collisions. So the two things we're looking at in this experiment are temperature and concentration. Now, we just saw that as concentration increases, reaction rate increases. And reaction rate increases with concentration because the number of collisions increases, okay? So you can go back and watch this video now. A kind of more kind of macroscopic, pertinent example of this idea of temperature here is this idea of hot dip galvanization. So I want to show you here, we're going to coat a key in metal and change its color by virtue of applying temperature to it. Okay, so this is another example of how temperature impacts reaction rate.
A common process used to galvanize iron and steel is called the hot dip method. Essentially, the metal is rinsed, dried, placed in a molten zinc bath, then quenched with water. While less industrious, we can use a very similar process to galvanize pennies. Then, with a little heat, turn the galvanized coating to brass. For this to work, we need shiny, clean pennies. Immersing them in a sodium chloride and vinegar solution takes all the dirt, grime, and finger oils off. They must be completely dried before the coating can be applied, or it won't stick. A solution of granulated zinc and zinc chloride is brought to a boil and the pennies added. The zinc in solution will plate out and coat the penny. This can take a minute or two, and the pennies might need to be flipped to completely coat the underside. When the reaction is complete, the pennies are rinsed in distilled water and dried. Now we have two fancy silver pennies. Because the penny is copper and it is coated in zinc, we can change the penny to brass by heating it on a...
Now here's the key thing. The penny is changing to brass by virtue of heating. You're trying to increase the rate of that solid state reaction. I say solid state because this isn't happening in a beaker. The reaction you're making go faster is really a combination of solid state particles trying to collide, and the way we're getting them to do that faster is by heating. And you can see as we heat this, the color of the penny changes.
Hot plate. You will want to flip it frequently to prevent burning the coating, but after about a minute, you get a shiny gold penny. Lincoln has never looked so good.
So kind of a neat way to make your pennies appear gold. You use this hot dip galvanization method. The key at the end there is you place the penny on the hot plate to speed up the reaction. Now, eventually the penny would turn to gold without heat, but it would be on a time scale that would be far too long for you to wait. So another interesting example of kinetics here. So with that in mind, I want to go back and ask another question about temperature and reaction rate. And I did this a little bit out of order, Dan, but thinking back to our hydrogen peroxide example, I want you to think about how temperature affects that. Could you put up poll question number 7, Dan?
Absolutely. I will attempt to.
Okay, well, that's all we can do is.
No promises.
All right. So here we go. Yeah. If we think back to decomposition, what would you do? You know, you just saw that hot dip galvanization. We sped up the coating of that penny and the color change to gold by heating. What would you do to slow down the decomposition of hydrogen peroxide? And I think we're going to have good results here, Dan. I think this is our class is going to think of this as like a softball.
We're getting there. Hey, Mike, while we're waiting the last 5-10 seconds here, can you give a quick definition on what galvanization is?
Oh yeah, galvanization is really, it's kind of coating a metal with another metal, and particularly it often applies to amalgams or alloys. So when you have different metals, you know, for example, copper and nickel, and you're trying to get them to come together or galvanize, you have to heat them. So that's the process you just saw there. We're kind of coating the penny in another metal by virtue of heating it. Ooh.
Great, thank you. All right, polls closed and results should be up there, Mike.
Okay, so yeah, use refrigerated hydrogen peroxide. So if you, next time you're in your science lab, I don't know when that'll be, but you might notice that your teacher stores the hydrogen peroxide in a refrigerator. And that's to slow down the decomposition. If anybody is still kind of a milk drinker, I have 2 little kids, they drink a lot of milk. Where do you store milk? You store it in a refrigerator. Again, that's to slow down the decomposition of the milk or the spoiling of the milk. Okay, so really, you know, refrigerators are a constant example of kinetics at work and how to kind of impede the progress of chemical reactions. Now, another part of this experiment had to do with temperature and reaction rate, and we were looking at the dissolution of a salt in water. So I want to show you a video that gave us our data for this next part of the experiment on how temperature affects reaction rate. And you already know, but here's another macroscopic example.
Let's compare hot and room temperature water. The first beaker is at 26 degrees Celsius. The second beaker is at 95 degrees Celsius. If we compare the 2 beakers with food dye added, you'll see that the dye distributes faster in the hot water. Why did this happen? The average kinetic energy of the water molecules is greater in the hot water than in the room temperature water.
So here you see that, you know, the solubilization of this dye wants to happen at a faster rate in the hot water than the cold water. So I think these are things we kind of know intuitively, that as we increase temperature, reaction rate increases. But always go back to like first principles is what we would say. Think of collision theory again. Think of bumper cars. I know we're getting a little analogous here, but if you heat something or speed up the particles and they're in a confined space, if they're moving very fast, the probability that they bump into each other is higher as their speed increases. So here were the data we observed with respect to effects of temperature. So we ran 3 trials. At room temperature, our salt, we saw some white crystals at the bottom, clear solution on top, so some solubility. And then as we increased the temperature of our water, we saw that most of the crystals dissolved. So generally, solubility does increase with temperature. In an ice water, we saw that dissolved crystals reappeared. Okay, so again, effects on and solubilization isn't necessarily a reaction, but temperature does tend to have that impact on dissolution. Okay, so now I want to flow. Last thing I want to talk about is equilibria. This is a concept that's sometimes connected to kinetics. And I want to just take a quick look at this equilibrium here. You can see it has a double arrow, which indicates that this can move in the forward direction and in the reverse. Okay, so now I just want to ask a question, a poll question, Dan. let's see. Can you ask before we watch the video, poll question 4? We'll talk about poll question 4. So if you haven't been exposed to this idea, it's called Le Chatelier's principle. Sorry, forgive my pronunciation there. But when you subject an equilibria to a stress, it moves to alleviate that stress. So I just want to get a feel for people's basic knowledge of equilibria. So see what you think of this question. This is a tough one, Dan.
It's close.
Close?
Yeah. Well, you kind of have a 50-50 shot here. Well, sort of.
Yeah, you know, it's some of my question writing ability is a little suspect as I look at some of these questions.
Well, and people that really, maybe don't have an idea, might have a favorite color and they just select it. So they may not even,
Well, that's true, Dan.
There you go. All right, we're just about there. We have 50% who think it's blue. Here's the rest of the results.
All right, so 50, yeah, the majority thinks blue, so good. So here's a quick introduction or refresher of Le Chatelier's principle. We're going to watch this in action. If I add sodium chloride to this equilibrium system, I'm really adding chloride ions. The system will shift in the direction to use up the chloride ions to alleviate the stress. So if this equilibrium shifts to the right to use up the chloride, the color will turn blue. Now let's look at actually a macroscopic example. So let's check this out with our eyeballs, okay? Can't do this in the lab. Lab's closed. So let's watch a video.
You just saw data on an equilibrium once equilibrium reverse breaks with color. Let's look at an example of an equilibrium.
So this is our cobalt equilibrium, and we're going to subject it to some stresses.
Equilibrium reaction that can be shifted towards the products or shifted towards the reactants. The initial color of the cobalt solution is light red. If HCl is added to the solution, the color will change to purple. The change in color shows that the equilibrium.
So Ashley there is calling that purple. I would call that blue. We have a little difference of opinion there, but she is adding, instead of NaCl, she's adding HCl. So you see how if we go back to our reaction, and we add HCl, this reaction is going to shift to the right to use up that chloride, and it turns blue. Okay, so let's continue with this.
Purple. The change in color shows that the equilibrium has shifted towards the products. We can make the equilibrium shift back towards the reactants by adding water. The shift can be seen from the color changing back to light red. This is an example of a system at equilibrium.
So there she's adding water and it's shifting back to the left. Okay, adding water and shifting back to the left. So again, depending on the stress, equilibrium will move one way or the other. Now the final question we have, Dan, let's end on a high note here with respect to this equilibria, is poll question number, let's see, and this is a tough one. Poll question number 3. Poll question number 3.
All right. Should be up, Mike.
Yeah, it's up there. So this is so look at the equilibrium on your screen, and what do you think? You add silver nitrate to this. What's going to happen?
We're a little slower to answer this one. We got a lot of thinking going on.
Yeah, this one takes a little more thought. This is one of my finer questions, Dan, I think.
I could tell by the lack of consensus here that it was more of a challenging question for you, Mike.
Yeah. So this is an indirect kind of effect.
We're really close on this one. Those 60 of you who haven't voted yet, give it a shot. All right, we'll give it 5 more seconds. And all right, Mike, there's the results.
All right. So, actually the majority answer was shift to the right. Now, if we add silver nitrate to this reaction, to this system, So assume this whole system is in a beaker or test tube. If we add silver nitrate to it, what's going to happen, and this is where I'm being a little mean, I think, the silver nitrate is going to go in, and the silver cations are going to interact with chloride and precipitate them out as silver chloride, excuse me. So the concentration of chloride is going to decrease because it's going to be taken out of solution by precipitation. So this equilibrium should shift to the left to counteract that stress. So kind of a tough one there, Dan. You can forgive people for that one.
You're not being mean. You're being challenging.
Yeah, I'm a soft touch, Dan. What can I say? So if we just the biggest thing in this experiment that I want to just reiterate, okay, you're trying to determine the effective concentration on reaction rate. This is like semi-empirical. You're not coming up with what we call a rate law, which you would really kind of quantify this a little better. But qualitatively, all we have to do, I mean, this is like scientific method 101 or science 101. We don't have to overthink this. If we have 3 flasks and we vary the concentration of our hydrogen peroxide across the flasks and control everything else, okay, we can see the effect of that concentration on the reaction rate insofar as how fast does it decompose. So again, if you had issues with the videos, I'm going to post those to the folder. You can go back in, complete the worksheets after this. The live lab, the live recording of this will be posted to the website, so you can use it as you see fit. At this point, I'd like to open it up for questions, and thank you again for joining us.
Excellent. Thanks, Mike. That was a great combination of instruction and video usage today. It's a great class. Before people start dropping off, like they've done a little bit in the past before the Q&A, I just want to remind everyone, we do have another session tomorrow on Thursday, and we're trying something new out. The topic is on chemical reactions, and we are doing an introductory course at 1 o'clock and an advanced one at 2. So you may want to pass that information on to classmates, fellow educators, and things like that. We're trying something new tomorrow. So first question here, Mike, that came across the board. Can you give some real-life examples of where this information is actually useful?
Yeah, no, I can. Well, again, I'll reiterate here, this is why you have a refrigerator. When you cook food, you're doing it at high temperature to make it faster. If we go to one of my favorite examples on the equilibrium side of things is this equilibrium I'll drop on screen here. And you gave me a chance to kind of talk about history here, which was my other kind of major in college. I don't know how rare that is, history and chemistry, but I did it. So, in the one of the more fascinating kind of equilibrium reactions, at least for me, is the Haber process, where we combine nitrogen and hydrogen to form ammonia. Now, nature does this, but we also do it inorganically, or we force it to create materials for fertilizers and whatnot. And let me just balance this. That's kind of the strict person in me, but this is one example. This is one of the more important equilibrium systems in all of agriculture, and therefore to humanity, in that it supports supply chains. But the interesting kind of history anecdote that I often hear about this, and if I'm wrong on this, you'll have to forgive me, but this was manipulated by a guy by the name of Franz Haber. He was I believe he was a Jew living in Germany right around the time of World War II, and he came up with a way. One of the big things that nitrogen is useful for is an explosive. So he kind of was able to optimize this process to churn out a lot of munitions for Nazi Germany. And then they found out he was Jewish and kicked him out. He came over here and said, "You guys got to be careful of the Nazis." So it's just an interesting backstory that dovetails with chemistry there. But this is probably one of the more important ones that I've seen.
Okay, great.
Sorry to be too tangential there, Dan. I couldn't help myself.
That's all right. It's appreciated. Why does the equilibrium reactions have 2 arrows?
Oh, that's a good question. Yeah. So if we go, for example, when you see the two arrows, it's a little, I think people get the sense it's a little kind of abstract, but if we look at something like H2 plus O2, and if I draw a single arrow, that means is that this reaction proceeds only in one direction, okay? It doesn't go to the right and to the left. It goes to completion in one direction, whereas two arrows denote that the reaction can proceed in the forward direction and the reverse direction. And when something's in equilibrium, though it's a dynamic process, as the forward reaction is occurring, so is the reverse reaction. So the two arrows mean that the reaction can go in both directions.
Got it. Thanks for explaining that further.
Sure.
This next question is kind of two parts. It's interesting. One of the students was observing closely. One of the experiments that looked like the hydrogen peroxide was reaction with smoking. What exactly was that?
Oh yeah. So if we, I think I can probably find that. If we go back here,
Visible.
and
You see how much
when you do, I'll spare you this, but when you do this at a high concentration, there's a ton of heat evolved when this reaction is done. A lot of energy is released when this hydrogen peroxide decomposes. And the decomposition products are water and oxygen. So what you're seeing there is essentially like some of that is water vapor. You're seeing that water being vaporized owing to the high temperature. Now we have to do this reaction in a borosilicate glass tube owing to that very high temperature. You might be able to get away with doing it in plastic, but we don't. If you do this in plastic, you start to see some fusion, some melting of the plastic because the temperature is so high. But that kind of vapor you see there, I think was the question, that's water. So it's not necessarily smoke as much as it's water vapor.
Great, awesome. I want to get our good chemistry friend here, Lenny, into the conversation a little bit. Lenny, if you can unmute and what were some of your takeaways from today and some of the chat questions that were going on that were answered?
Again, really good. Hello, everybody. I guess I have really good questions being asked. A lot of it was dealing with the videos that you were showing. They were very involved with that. The rate of the reaction, the formation of the bubbles showing more foam being a faster rate was observations. They were asking more about Le Chatelier's principle and what it really means. And it's a tough thing to discuss in a short amount of time. So that was one thing they were really interested in. So I'll leave you with that one.
Oh, okay. Well, here, let's just talk another minute on that, Dan, if we could. Le Chatelier's principle.
Yeah, we have time.
Yeah, so let's draw this one, and then I'll go back to my little ammonia example. I'm a big fan of the Haber process. It's responsible for so much stuff. So if we draw this equilibrium up here, okay, and this is an industrial process that occurs every day, super important to our food supply. Here, let me just make sure I balance this. So Le Chatelier's principle says in any equilibrium system, if you stress it, it's going to shift in the direction to alleviate the stress. So in a stress can be something like I add more reactant. So let's say my stress is I add more nitrogen, okay? Now this equilibrium is going to shift to reduce that stress. So if you add more nitrogen to this equilibrium system, it's going to shift to the right to use it up. It's going to try to get back to that baseline state, okay? Whereas if you take nitrogen away, if you take it away, okay, this is going to shift to the left to make more of it, to alleviate stress, okay? And there's various stresses you can apply to an equilibrium, and people will apply these stresses to optimize production of things like ammonium. You can change pressure, change temperature, change concentration, okay? But again, it's what can I do to this system to make it move the way I want it to move? I can take nitrogen away, I can add nitrogen, I can take hydrogen away or add it, I can take ammonia away or add it. I can do this in a high pressure reactor and increase the pressure to get this to move one way or the other. Or I could increase the temperature. So it's really kind of optimizing yields in industrial processes.
Great, excellent. Hey, Mike, we had a bunch of people join a little bit later than like
Sure.
3 minutes in when you were doing your demonstration. Could you just go back and show folks where those videos are again really quick? We had a lot of IT questions here in the chat about, can I use them in class and things like that. So that you can review them and use them in class on limited views, but if you could show them where to get those once the session's over, I would appreciate it.
Sure. So if you go the end of this and go here, I'd encourage you to just go here and explore too. I'm going to pop open an internet window and I'll show you how to get this just from our website. That's probably the easiest way. If you go here and you'll see we have this big Flynn at Home Science sign, you can click Explore Now here, or you can click the hyperlink up here. Either one will take you to what we call in the marketing vernacular a landing page. We'll learn that in my time at Flynn. And then all of the stuff for these live labs are housed in this at-home live series page. So if you click this, now you'll gain access to the different live labs, okay? And if you're looking for the materials, the videos, okay, they're in two places. If you're a teacher, you can click Teacher Materials. If you're a student, click Student Documents, okay? And this will take you into a Google folder. Now, the videos live in here. And then also all of the individual videos, okay, the PowerPoint presentations are also in here. So you can go back, you can take those videos out of the PowerPoints, download them on your machine. You can kind of, put them in your own folders, whatever you want to do. But we have a kind of an introductory video that pairs with each lab here. And then the presentation is just in PowerPoint format. This is just a way of housing all those videos in individual form. So you can pop that open and watch the videos on an individual basis, play them back, whatever you want to do. And then again, if you're a student, these worksheets, these are all in Google Doc form. So you can come in here and if you'd like, you can make a copy of these. Now, when you make a copy it into your own Google folder, and then you'll be able to write directly in the document or change it. Alternatively, you can download these as Word documents or PDF documents for printing, et cetera, et cetera. But yeah, a lot of different ways you can use this. If you're a teacher, and I apologize, I exited myself out of the window there. If you're a teacher, what I would advise is go to our webpage here, and you'll see we put together just a short video here. It's about 1.5 minutes, 2 minutes that'll tell you some kind of ideas for how to incorporate these into your lesson plans. Because again, if you miss the live sessions, you can access the recorded versions here. And then you go back here, we have another 5 that we've run over the previous weeks with all the documents. So, again, if you can't do these live, no problem, do them on your own time. We give you all the data. We give you the worksheets. The only thing we don't give you is the physical equipment. Be hard for us to do that. So that's where all that stuff is, Dan.
Wonderful, Mike. I appreciate that. So that brings our session to a close. As a reminder, we really want your feedback, educators. So please hit us up on email at flynn@home@flynnsci.com, and we would love to hear from you. And then another reminder of our 2 sessions tomorrow on chemical reactions, 1 p.m. Central Standard Time, introductory to it, and at 2 p.m. Central Standard Time, more advanced lesson on chemical reactions. Thanks everybody for attending. Please connect with us on Facebook and Twitter at FlinnScientific. Thank you for attending. Have a great week, and continue to practice social distancing. And have a great rest of the day. Take care.
Bye, guys.